Okay, all right. Okay, thanks. Probably my first seminar in the church, so try to be worthy. Okay, lesson from sample models. Good. So unless you're living in a cave or something, you probably know that we are living exciting times, and it's not an exaggeration. But yep. Oh, here, that's good. All right, I have a weird echo here, but I'll do my best. Okay, so you probably realize that we are living exciting days. We live the days of the machine learning revolution, and we are seeing everyday computer doing things that were completely impossible to do merely 10 years ago. Just a few examples. This is a text. I don't know if you can read. I wrote the part in black. Thank you, and I thank the conference, the MECO, to give me the opportunity to give this talk here in Erice. Today, I would like to talk about the research in statistical physics applied to theoretical machine learning. As you may have heard, and then a computer, an algorithm, filled the rest. And you can see that the computer stayed on context. It starts to describe what machine learning is and how it's used in these days. Okay? That was done by an algorithm called Muse, developed by a startup I founded 2 years ago in Paris. Now, that kind of thing was impossible 10 years ago, and now it's routinely done. The computer can go on and give a talk slightly different from mine, but it could. Yeah, you are probably missing part of this. Every day, there is something new in my, on Twitter, and I'm blown away by what a computer can do. But it's another example. It's text-to-image generation from Google. You basically describe what you want to see. On the left here, you have a text that says a teddy bear swimming at the Olympic 400-meter butterfly event. And the algorithm is drawing a teddy bear swimming. This is a chocolate cake. You cannot see the prompt. By the way, you have a zoom problem here. I will do my best. Saying a chocolate cake with the shape of a bald eagle, and it's doing it. And it's really amazing. Okay, and every week there is something new, and it's even more amazing of what happened the week before. So it's really hard not to be impressed by all of this. So the question is, can statistical physics say anything about that? Okay. Now, of course, statistical physics has been connected with machine learning since a long time. I mean, since the 80s, with the work of Hopfield and Elizabeth Garner, Emerson Polinsky, Amit, and all those people. But these days, we are, this is a mature engineering science. And can we still try to be relevant? And I hope the answer is yes. I think most of the talk this morning will be in this direction. So hopefully we need to step up and see what we can do. Now, why statistical physics can bring something? Well, part of the reason is that if you just go to speak to your colleague, or at least if you did this, you're missing most of my jokes here, but it's okay. If you went and speak with people in a stat department or theoretical machine learning department merely 10 years ago, they would say that they have all it figured out, and everything was firmly based on very strong principles, the pillars of wisdom. One of them was, okay, we need to use convex function because they are easy to optimize, and we know we have guarantees about how to optimize them. They will tell you that you have to be careful about how many parameters you use and to beware of the Bias-Variance Trade-of. And they will tell you that they have statistical guarantees that were mostly low dimensional. Okay, so neural nets have completely destroyed this vision. Now, all these pillars have been completely shattered. We are not using convex function, we are using neural nets. These are highly nonlinear complex functions. They are completely crazy functions. There is no Bias-Variance Trade-of. Apparently, you're using as many parameters as you can and it still work. And you're not working in low dimension. You are working with high dimensional objects, a lot of data, millions of data points, millions of parameters, and getting close to billions these days, and it still works. Okay, and so part of this discussion is where maybe our community can do something. So in this talk, I will basically discuss this pillar, the question of overparameterization. I will also discuss a bit the high-dimensional part. And I will leave the part of learning nonlinear complex function, but that will be discussed by many people today. Actually, it's talk by Bruno Loureiro discussing this. There is also a poster by Francesca. And the next talks by Jean and Carlo are also discussing such. All right, so let's move on. The first thing I want to discuss is this question of overparametrization. Bias-Variance Trade-of. All right, so let's go back to the roots. The simplest thing you can do in machine learning is classification and regression. You are given a bunch of points and you try to predict something. So for instance, you have the x-axis, the y-axis, you have these points, and someone is asking you, if I take this new value for x, what is y? Okay, that's the way it works. You make a fit. Oops. Really just fit the data. And you say, fine, now I have a fit. I project, and this is my new estimate for y. Okay, so that's really as stupid as this. In fact, you may even say that machine learning is just glorified curve fitting. And that's kind of true. That's really what it is for the supervised part. Okay. Okay, when we were taught this stuff as kids in the university, we were told we have to be careful with the number of parameters of the function we use. Okay, and we're usually given this drawing. If we use not enough parameter, well, we are going to do a stupid fit. If we use too many parameters, we are going to overfit the data, which is probably noisy, so we pick up too many detail. And it's really, really fundamentally important to be right in the middle. Okay, and the entire theoretical construction was made to try to understand this. All right, so these are very reasonable expectations. A lot of math behind it. The truth is that this is not the way it works with neural net. Okay, as far as neural net is concerned, the more parameters, the better. Let's see if oops. That's kind of disappointing. It's a bit anticlimactic. Oh, that's even worse than this. Okay. Good. All right, so this is an experiment that was done by my colleague in EPFL, Mario Geiger. It's in the group of Mathieu Eviard. This is the performance of a neural net. Here you have the number of parameters, and here you have the generalization performance. Okay, the data on performance on unseen data, and you have this weird behavior. It's you increase your number of parameters, it gets better, then it gets worse. Good, but then it gets better again. And here you have really huge number of parameters, and it still gets better and better and better. That's not an isolated observation. This is something you see all the time. That's an experiment done by the group of Nakiran et al. And you see the exact same picture. And you have two very interesting phenomenon here that I will discuss. Interestingly, if you dig the physics literature, that kind of thing were already described. There is a beautiful paper by Manfred Hopper and by Krog and John Hertz in the 90s who discussed similar things. So, physicists are clever. So this phenomenon, when you first go down, go up and go down again, it's called the double descent. Very dramatic name. And there are two interesting things here. Okay, the first one is you really, really have a huge number of parameters and you still do not overfit. The second one is that apparently there is kind of a bump, a cusp, or a peak, if you want, around here. And I don't know if you can see, but this is where the training error, that's your quality of fit, is going close to zero. So why is this? Can we understand? That? All right, so this is stuff. And so we have to start with sample models. And this is what we have done. We have looked at the simplest possible example for neural network. I mean, you might agree, you might argue that we can do simpler, but this is simple enough. So it's a two-layer neural network, but I'm not learning the first weights. Those I keep random once and for all, okay? And I'm only learning the second part. Okay, that looks too simple, and it kind of is, but it's not ridiculous. There are many reasons why you would want to study this. First of all, this is a very valid method. It's called the random feature network, and it's widely used. Very popular method in machine learning. Actually, the people who push for it, Ali Raimi and Benjamin Recht, got a test of time award for this paper. So, if it is good enough for the machine learning community, it's good enough for us. You can actually show that if you use that kind of architecture, you can recover all the results of kernel methods, all the results of Gaussian processes, and many other methods. So this thing encompasses a large number of methods of machine learning. And you can also show it's even equivalent to multi-layer deep learning neural network in some regime. Let me explain this. So if you take a multi-layer neural net, like this one, and you look at the size of the intermediate layer and you make it really, really big, okay, and I mean really, really big, then you can show that in this limit, what you learn can be rigorously mapped to that kind of model in which the first layer is fixed and you only learn the second layer. Okay, so it's not such a bad model. In fact, some people started to claim that if we understand this, we understand everything in machine learning. I violently disagree with this. I think this is not true. This is really too much simplistic. And I wrote a paper about it if you want to read about it. However, what I agree that if we don't understand this, we're not going to understand the more interesting stuff. Okay, but it's important to remember that this leaves out a lot of interesting stuff, which is the feature learning regime that will be discussed, I think, by Jean and Carlo just after. Okay, so all my talk will be on this model, on this architecture. Okay, good. So what do I want to know? I want to see if I can understand this bias-variance trade-off with this. So this is what we did, and that's the kind of statistical physics approach. So we take data and data point. Our data points are just Gaussianly random vector, okay, random data. Now we have a function f0, which I'm not giving to you, but there is a function that creates a true label, okay? f0 is creating the label y for this data. Now I'm giving y and x to my neural network, and I'm asking it, okay, try to learn what is the function. And the way it does this is by minimizing what is called the cost function. There is a loss. There is a choice of what you here. You can use a square loss, which is a square difference between what you predict and the truth. There is a logistic loss, the hinge loss, a lot of different possibilities. There is this term here, which is fundamental. Try to remember. I'm here basically putting a penalty for a large norm. Okay, and this is called the regularization, the L2 regularization. So that's what people do. The question is, okay, if we send d, p, and n to infinity, so n is the number of a data point, d is the dimension here, p is the dimension here, they all go to infinity. We are in a thermodynamic limit, as we all like. Can we analytically compute what is going on here? And the answer is yes, we can. This is how it looks. Okay, so nice equations. So these are fixed point equation. We have 10 parameters. And if you solve the fixed point equation, then at the price of a two-dimensional integral, I can give you the generalization error. I can give you the training error. I can give you this number. Okay, it's an analytical solution that's been a lot of work, not only by my group, something that many people worked on. And where does this come from? Well, of course, oops. Yeah, yeah, okay. So you see it's not completely random. I don't want to describe this equation, but the loss is there. There you have the function L0. Somewhere you have this G mu. G mu is the Stieltjes transform of FF transpose. So of course there is some random matrix theory in it. And you can see here you have some numbers that depend on sigma, which is the activation function. So all this stuff enters the detail of the fixed point. Okay, and all this is coming from statistical physics method. Actually, we first derived this using the replica method, which was very interesting. And then because not everybody is like you in this room, not everybody believes in replica. So we also proved it using rigorous method, in this case, combination of Gordon minimax and random matrix theory and probability technique. So We understand everything there is to understand on this thing. Okay, this is how it looks like. In this model, if you increase the number of parameters, that's what the training error looks like. Okay, this is for two different loss. This is L2 loss, this is logistic. At some point, you have a perfect fit. And in terms of prediction, well, you have a peak. If you use logistic, it's here. If you use L2, it's there. And then it decays. And indeed, you don't have this weird problem that, of overfitting. So it's great. We can reproduce everything with a model, which is what we physicists like to do. We like to make simplistic model and reproduce things. Now that we have a model that reproduces what is going on, can we understand what is actually going on? Okay, which is try to interpret our finding. Oops, I'm inverting my arrows. Okay, so these were the two questions we were interested in. So let's go with the first one. Why is there no overfitting even where we have a huge number of parameters? Okay, why are we wrong? Okay, so let's go to a simplest case. Let's take the blue curve, which is the square loss. Let's take lambda to 0, so no regularization. So we are just minimizing the square difference between what we predict and the truth. What is going on now? Well, when I am increasing the number of parameters, I have, better and better functions. And if you look to your energy loss, it gets, better and better. You can go to lower and lower value of training. When you have P, the number of parameters, equal to N, the number of data, then you can fit perfectly. In fact, you can do, by matrix inversion, it's a linear system. And when you have more and more parameters, then you have a larger and larger region of zero energy. Okay, and if you draw this region, you go from under-parameterized to over-parameterized, and you have this set of zero energy solution. It's non-existent. Here you have a point, and then it grows and it grows. And since it is a very simple model, the thing's still connected. You don't get the complex stuff we get with a real neural network, but that's still interesting. Okay, good. So now let's pick a solution at random. If you are Bayesian, that's what you would do. Oh yeah, I will pick a random solution here. Okay, I pick a random solution, this one. And let's see how it works. Of course, it will go to 0. In terms of training, it's going to be super good. How does it work in terms of generalization? Well, we can compute it. This is what it gives. Okay, it's terrible. So if you pick a random solution, it's terrible. So, the bias-variance trade-off is not complete bad. It's telling you, yeah, it's true. You should not do this. But the truth is that that's not what you do. Nobody is picking up a solution at random. You're not sampling this stuff. That's not what anybody is doing. You're using a specific algorithm. For instance, I fooled you here because what I did was to say, haha, I have this lambda, this regularization, and I send lambda to 0. I didn't take lambda equals 0. I send it to 0. Now, if you do this, what you have is actually what is called the least norm solution. Between all these solutions, I pick up the one which has the smallest L2 norm. So in terms of vector, is the shortest one. So I'm really biased in the way I'm choosing solution. If you send directly lambda to 0, what you will do, if you ask a computer to solve the problem, is using linear algebra, you would use Moore pseudo-inverse. But the Moore pseudo-inverse is also finding the least norm solution. Okay, but that's not what you would really be doing. What you would really be doing is using gradient descent. Okay, but gradient descent, it depends where you start. It's not something that, simple. If you start anywhere in Sicily and you try to do gradient descent, you are going to end in the zero energy state, which is the water. You're not going to end in French Brittany or in Antarctica. You're going probably, if you start here, you fall here and will be somewhere on the coast. And if you start here in Erice, somewhere there, you're going to end up somewhere here. So it's also a very biased procedure. Okay, it's not sampling. In fact, if you start with very small weights, you'll also find the least norm solution. Okay, and the trick is the least norm solution is a very particular solution here, and this is the one that generalizes well. Okay, and we can understand that from the equation, and there are very good theoretical reasons for which this is the right thing to do. And That's the thing. There is no violation of the variance trade-off principle. Instead, there is always a regularization. Sometimes it's explicit because I'm saying, oh, I have lambda. Huh? And sometimes it's implicit. But just by using gradient descent, we are regularizing the problem. We are selecting solution. And we are sort of lucky that this algorithm works. Okay. Now, you may wonder how this translates into more complicated problem. And the belief is that for some magic reason, gradient descent, even in more complicated network, is biased toward good solution. And there are a lot of exciting ideas there, especially from the statistical physics community around the group of Riccardo Zecchina, who is pushing, for instance, this idea of bias toward the flat minima. So that's nice. We can understand this phenomenon. Okay, let's look at the second one. So we had this peak. Can we understand this peak? Why this thing is peaking there? So it turns out you can, and that's a set of work that we have done over the last 2 years. It started with some replica analysis with Giulio, Stefan, and Maria. And recently we revisited this with Bruno, Cedric, our beloved organizer, and Maria. And we actually managed to prove everything, so that's always good. So the point is the following. This generalization error that you see up there can be decomposed into 2 different terms. Okay? And you have to be careful about how you make the decomposition. And I'm going to argue that there is an approximation error that you can call bias if you want. And there are fluctuations, which are variances. But this decomposition has to be made in a very proper way. Okay, so let's go back to our model. This is what I used as a fitting procedure. Okay, but here I used weights that were randomly drawn. They are all taken from a Gaussian, from anything else, actually. They are taken from one realization. What happens if you use a different draw of the matrix? So what if I take my data and I have the first draw of my random matrix, I have my features and I fit, and I have a second draw of the matrix, and with this one, I have my features and I'm fitting. Well, obviously, I'm going to have short fluctuation. These 2 predictions are going to be slightly different, right? Because that depends about the precise draw of my random weights. Okay, so what we did was basically to try to characterize exactly this solution. So if you do this many times, not only once, twice, many different draws, and you call the field that comes here before the last activation, not really important, but the last number you get, call it H1, H2, call H star, which is the true value. What we can prove is the following. All these numbers are basically Gaussian. Okay, they are jointly distributed Gaussian. They are Gaussian covariates. And if you want to know what the covariance is, well, you have to solve again some mean-field equation given by replica that we also can prove. And well, that's nice. Now, what do I mean by bias and variances? Well, the bias is given by the average of all of this. If I would repeat this an infinite number of times and average everything, I would kill entirely all the fluctuation coming from the different draw of the matrix. Okay, that is the thing I call approximation error. What is left, the variance of H, is entirely due to the fluctuation and to me, when I learn with a given network, fitting and the precise distribution of the draw. And once you know this, well, you can try to decompose the error into terms and to plot it. So again, that's the generalization error. It goes down, peak goes down again, more parameter, and it decomposes into these 2 terms. The blue is the approximation error, and you see that the approximation error, the bias, what you will get if you average all these fluctuations, is monotonically decreasing, at least if you use a L2 norm solution, blah, blah, blah. If you use a randomly chosen solution, it's going to be bad. And it has actually a phase transition exactly at interpolation, and it doesn't get better. Once you have enough parameter, if you kill this fluctuation, you have the best you can get. The red term, however, is the variance. And you see that the variance is what makes you overfit. Why? Well, it makes sense. When is the point in all the story where you are more sensitive to the exact realization of the particular draw you did? Well, it's exactly when you start to have a zero energy solution, because you have only one solution, you cannot choose, and you are completely overfitting the exact detail of the first layer. And this is why you have a peak here. But when you get more and more parameter, essentially you are starting to average this situation. Okay, you can think about how you prove self-averaging in physics. You know, you cut your system and then there is a correlation length and then you average. That's literally what's going on here. Okay, and so that's very nice that we can understand this phenomenon. Okay, and just for the fun, if you go in the literature of machine learning, people are like, oh yeah, this is brand new, and nobody knew this and everything. And everybody is citing the same paper from '92, this paper actually, to say that neural network were obeying the variance bias trade-off, the original one. And in this paper, if you read it, they look at tens of different variant of methods, and indeed they all random forest, whatever, and they all have a nice bias variance. But these are the data for the neural network. This is what they show, and that's the total error. They do a bias variance decomposition, which is the same one I just did, and they have a flat transition here and the variance that peak here. And what they actually said is, well, we probably did something wrong, more work is needed. And then for like 30 years, everybody cited this paper to say, of course, neural networks are obeying Bias-Variance Trade-of. And in fact, it was staring at our face. This is their plot, this is our plot. So you see, it's very similar. Okay, so there will be much, much more to say here, and I will be happy to tell it to you, because I gave the discussion about the L2 error. It's slightly different with logistic and hinge and SVM. There is a connection to committee machine and so on and so forth. But that will be a story for another time, because I want to discuss the last point, which I think is interesting for us. Okay, so that was my third pillar. The question is that now we are not in low dimension. We are not using classical statistics where they basically do some worst case analysis with low dimensional data. We're in high dimension. So it's called, why should we care about Gaussians anyway? Everything I just said was, typically of statistical physics paper. The data are Gaussian random variable. This is ridiculous. Okay, I mean, that's kind of ridiculous. If you go in a stat department, people will laugh at you. I know this. Don't ask me why. Because real data are not Gaussians. Okay, that's not what we do. You're not given random Gaussian to fit. That's how real data looks like. If you are doing cats versus dog classification, you have picture of cats. These are not Gaussian cats or Schrodinger cats, these are cats. If you are doing a face competition, you have picture of faces. That's the kind of thing that you find if you go on Kaggle and you play this game. Even if you are really lazy and take the simplest possible data set, which is MNIST, well, you have digits. How digits look like. These are not Gaussian data. And it's very nice to make this nice plot with Gaussians, but maybe it's completely out of touch with reality, and you might have some people telling that to you. Okay, so let's see if it is out of touch. Right? Let's try to see how our beloved ghost is different from them in nature. So these are some Gaussian random pattern. And this is a real data set. It's called CIFAR. There's 10 different categories of planes, horses, boats, and everything. And how different are they? Well, they look different to me, for sure. So this is what we are going to do. Let's do some numerical experiment. I'm taking my favorite model, this model with random weights, and fitting it some real data set. And I'm trying to see what it gives in simulation. And then I'm going to fit some Gaussian data, and I'm going to see what it gives in simulations. Okay, and since I want to be fair, I will use for my Gaussian data the same covariance as a real data set. Okay, otherwise it's a bit ridiculous. Okay, and what do I take for the labels? So I'm going to do what physicists did first in the 80s, which is to use random label. Okay, so For each of these points, I will take a random label and I try to see the training error, and I will do the same with real data set. Okay, and if you want to know what it means instead of working with the real labels, I'm permutating them. Same permutation. Okay, and that's really a physics thing to do. In fact, that's the kind of thing that were done in this amazing paper. It's the most important paper in our field by Elizabeth Garner and Bernard Derrida, because it's a very important question. You know, if you have data like this, how many data can you learn? How many can you fit? How many patterns? Blah, blah, blah. Okay, and it's not just statistical physics question. Random label is really fundamental if you do statistical theory of learning, connected to Rademacher complexity, VC dimension, and so on and so forth. Okay, so what happens if I do this? How does it look? Okay, so here we have 4 different data sets: MNIST, fashion MNIST, CIFAR. Here you have Gaussian mixture of many, many Gaussians together. The points are simulations. This is error as a number of data points. And the line is the Gaussian prediction. Okay, the Gaussian prediction when n and p is infinity and everything. So not only our prediction should be ridiculous because they are Gaussian, they also should be ridiculous because they are at infinite size in the thermodynamic limit. However, when I plot the two together, I don't know about you, but doesn't look too bad. Okay. Here I'm just matching the covariance of the data. Now, this is with finite lambda, finite regularization. If I send the regularization to 0, I have a collapse of all these curves to 2 master curves. Okay. So this is for the ridge error. Ridge means I'm doing the square loss, or y minus y true squared. And this is the training error. The line here is analytics. There is even a formula. I think it's 1 minus 1 over alpha or something like that. And this is for logistic or hinge, or sorry, logistic, and you have 0. The transition is at 2, which you should know if you read the paper by Elizabeth Garner. While here the transition is at 1. But again, all these massively different real data, they all collapse on the same curve. So yeah, I will call this a good agreement. So this is reassuring. You know, maybe it's not completely crazy to do a Gaussian assumption. We may wonder, why is this true? Okay, can we understand why is this true? Because both stuff is massively different. Okay, so we tried to answer these questions, and it's hard to make a theory for natural images because what is a distribution of natural images? I don't know that. I mean, I can download them on internet, but it's not really good. So we did the next best thing. We said, okay, let's take the distribution of images that are generated by neural network when they generate things that look natural. Okay, if you're following a bit of machine learning, that's called the generative networks. Let me tell you how it works. This is how neural network would be trained to generate picture like this. Let's say you have 4 categories, dogs, land, butterfly, and hamburger. You will start with a Gaussian noise, and you will take your noise taken from a Gaussian distribution with mean and a variance that depend on your category. Okay, so you have 4 Gaussian clouds, and you take 1 point here. Then you feed this into your neural network, and it produces an image. Okay, there are many ways to train this network. Some of the most popular ones are called normalizing flow and GANs. But let's say someone is giving us this network. Okay, so that's the way you do things, and it works amazingly well. Just an illustration. These are GAN-generated images of burgers, mushrooms, and pizza. They don't look like Italian pizza, but okay, maybe it was trained in Chicago. And these are real images, and it's extremely good. Okay, so fine. Can I make a theory of what will be the error if I use data generated by the network? That is a precisely stated mathematical question. Turns out we can. Good. And we came out with 2 theorems that I'm going to state to you. Theorem 1 is basically saying, like, if you generate data like this, okay, from a neural network, or if you generated data from a mixture of Gaussian, not a Gaussian, okay? So from a mixture of Gaussian, one Gaussian by category, then we can prove by the miraculous effect of high dimension. So think central limit theorem if you want, even though it's a bit more complicated than this. We can prove that on expectation, the error will be exactly the same and will go to the difference will go to 0. That's a very strong universality statement. And that's very, very nice. It's something we just did in this paper with Federica, Bruno, Ludovic, Stefan. And it built on many, many results from the community. In fact, I just need to mention this fantastic paper by Romain Couillet and his team, who started to address this question with random matrix theory. So that's nice. But here I'm using the real labels, and I'm proving that mixture of Gaussian is good. But what happens if I use random label? Okay, that's something that we would like to do, because so far we prove real data can behave like mixture of Gaussians, not Gaussians. Okay, well, that's our second theorem. If you're using random labels, then you can directly replace this model by one Gaussian with a matching covariance, and then the training error is also the same. Okay, so we were really, really pleased by these two theorems, and we were really, really pleased, first of all, by the empirical observations, because basically saying that, if we are in high dimension, it's sometimes okay to use Gaussians or mixture of Gaussians. Now, of course, this is true only for the sample architecture I described, the one with fixed features and everything. But that's nice. That's nice because we should not be ashamed of what we do and of modeling things. Okay, and this is where high dimension is changing things from the theory point of view, I believe. Okay, so it's time to conclude, I think. So can statistical physics say anything useful about this? Well, I certainly hope so. I gave you some example, and you are going to see much more during the conference. Let me just summarize what I told you. So there is some high-dimensional magic that's changed things. Gaussian models are really good. If you want to keep the real labels, actually, Gaussian mixture are even better. And at least, if you're using this fixed feature or random features model, these are really, really good approaches, and statistical physics is relevant, especially because once you do this assumption, well, you can actually compute with statistical physics techniques and then prove, if you're into that sort of things, mathematical physics techniques, exactly what is going on, and that's very nice. Okay, I think it's kind of redeeming a bit the approach of physicists here to the community of people in machine learning. And in particular, I showed you the result of such analysis for this problem of over-parametrization. Okay, and you see that we can, use this model, use reasonable assumption, solve them, and then understand what is going on. And in this case, we could see exactly how implicit regularization mitigate overfitting, and we could characterize the decomposition of the error into bias plus fluctuation. Okay, I think I'm done. There will be much more to be told, but that will be a story for another time. Let me just thank all my fantastic team that have been working on this topic in EPFL, and shameless advertising. Anyone's looking for a job, but Switzerland, it's maybe not as beautiful as Sicily, but it's not bad either. And write me a mail. Thank you.
Okay, we have time for a couple of questions. Hi, very nice talk. I have a question about this Gaussianity concerning the natural images, because I was thinking this result works only in the asymptotic limit. So isn't like a glorified version of the central limit theorem?
That's exactly what you would say if you don't know anything about probability, yes.
Oh, okay.
But it's not. So for very deep reason. First one is, if you take a random vector and apply it to the natural image, then you get CLT. And that's one part of the approach. Now, the problem is here. you are not using a random vector. You are using a vector that minimizes what you have seen with the images, which means you are extremely correlated with the images. And the fact that these things stay true, even though you start to have correlations, is really non-trivial because all the assumptions that you make in the CLT are completely break down. And so this is where things start to be interesting. And secondly, when we use this, you could do this, say, okay, I don't care about this correlation, but then you will get this mixture of Gaussian. Now going from the mixture to a single Gaussian, it is even harder. And the way we did it was basically the statistical physics way. We did a computation with replica. We realized it was true at the replica level, and then we proved the replica computation. And so the theorem 2, I suspect there should be a deep probabilistic reason behind it, but I don't know it. The way we proved it was really in a statistical physics way. So yes and no.
Hi. So maybe it's well known, and this is an outsider question, but you use these two-layer networks where in the first layer the weights are quenched.
Yes.
So how does the picture change if you consider a different a priori distribution for these quenched weights? Because I guess you are using also Gaussian there. So if you use a heavy tail distribution for those weights.
Yes, good question. So as long as, so if you take this the matrix, and as long as the weights have the eigenvalues or the singular values have a compact support, then everything goes through, and it depends only on the Stieltjes transform. Now, if you start to have heavy tail, there are some very, very interesting phenomenon which you actually looked at because it's connected to the kernel limit. It seems that many things go through, at least from statistical physics point of view. From math point of view, it's harder to have control because things start to depend on the tail. But it seems that most of the analysis goes through, and that's a very important point that we should be. And it's not academic because when you start to go to the kernel limit, that's really what matters.
What's so special of the boundaries of your Bayesian of solutions? I mean, because you say you end up there.
That's just a sloppy drawing. I mean, this is high dimension. I don't know to draw things in high dimension. It's really bad drawing because everything is a boundary. Bad plotting, but I don't know to make plots of dimension more than 2, unfortunately. So, no, they are all close to a boundary of something, all the solutions. Now, what's really special about L2 norm solution is, okay, that I can tell you. What you can prove, and it's 2 lines computation, it's very easy, is that the weights you are learning can always be decomposed by a part that has seen the data plus in the overparameterized regime, something that is not connected with the data at all and can be arbitrarily big. So what should you do? Well, you should take the second part and crunch it to 0. And if you do this, you actually get the least norm solution. And that's what people do when they do kernel, by the way. I mean, this is called the representer theorem.